Good afternoon, everyone. So, we are in this class we will be looking into the specific examples of eigenvalue problems and how these eigenvalue problems will be used for solving the chemical engineering application oriented process equations. So, we have already seen one example in the last class that how to solve a non-homogeneous set of homogeneous set of non-homogeneous algebraic equations. We have taken up two examples. In the first example, the eigenvalues were real and the solutions and all the elements of the eigenvectors are real, and you are getting a real solution of the system. In the next example, we have considered a problem where the eigenvalues were imaginary. So, therefore, the elements of the eigenvectors are also imaginary, but ultimately you will be getting a real valued solution as a final answer, because the chemical engineering problem that was that we have been considered, they are basically real of real valued. Next, we have taken up the theory for solution of a set of homogeneous ordinary differential equations, and we have taken up an example. We have developed the theory for it, and we have taken up an example how to solve them, and we are almost at the last step of the solution. So, if you remember that we have the initial value set of the conditions where 2 and 3. These are the initial value problem at time t is equal to 0. These are the values of the variable, and we were looking into the solution, and that for the solution you are going to get the coefficients C I naught, and these coefficients are defined as the inner product of x naught and y I, and divided by inner product of z I and y I. If you remember that y i's are the eigenvectors of coefficient matrix transpose of coefficient matrix A transpose, and z I were the eigenvectors of A, So, therefore, this will be nothing but x 0 transpose y I z I transpose y I, and C 1 0 becomes x 0 inner product of x 0 y 1 divided by z 1 inner product of z 1 and y 1. So, this will be x 0 transpose y 1 divided by z 1 transpose y 1. So, the coefficient C 1 0, if you remember x 0 transpose, where it was 2 3, it is the transpose of the vector 2 3, and y 1 is nothing but eigenvector 1 1 divided by z 1. Z 1 was the vector 2 1, and this will be y 1 will be 1 1, and this will be 2 plus 2 into 1 2 plus 3 into 1 3 divided by 2 into 1 plus 1 into 1. It will be 5 by 3. Similarly, we have already seen that C 2 naught will be the inner product of x 0 t y 2 divided by z 2 t y 2, and this will be 2 3, and it will be y 2 will be 1 minus 2 divided by 1 minus 1 and 1 minus 2, and ultimately it will be 2 minus 6 divided by 1 plus 2. So, it will be minus 4 by 3. So, we were able to estimate the coefficient C 1 and C 2, and then we have solved almost everything, and all the quantities are known to you. Now, we will write down the final solution. The final solution will be, if you remember, the final solution is in this form. Final solution becomes x1 x2 is equal to C10 e to the power lambda 1 t z1 plus C20 e to the power lambda 2 t z2, and if you remember, the thing becomes the lambda 1 turns out to be we just put the values of lambda 1 and lambda 2. So, this becomes x1 x2 is equal to C10 e to the power lambda 1 t, and this becomes z1 was 2 and 1, the vector of 2 and 1, and this becomes C20 e to the power minus 3 t, and z2 was 1 minus 1. So, therefore, the x1 and x2 becomes, put the value of C1 is 5 by 3, lambda 1 was 0. So, it will be 1 and this will be 2 1 plus C2 will be minus 4 by 3 e to the power minus 3 t 1 and minus 1. So, therefore, we can construct the final solution as x1 is equal to 5 by 3 into 2 minus 4 by 3 e to the power minus 3 t times 1. So, this becomes 10 by 3 minus 4 by 3 e to the power minus 3 t, and x2 becomes 5 by 3 into 1 minus 4 by 3 e to the power minus 3 t multiplied by minus 1. So, it will be 5 by 3 minus plus 4 by 3 e to the power minus 3 t. So, that is the final solution of whatever the problem we are looking into. So, this gives a direct application of eigenvalue eigenvector problem to solve the set of ordinary differential equations which are homogeneous. Now, let us talk about the advantage of this method compared to any numerical scheme. If you look into the numerical scheme, for the numerical scheme, you could have preferred any integration subroutine to solve this type of problem. These subroutines include Runge-Kutta 4, fourth order, or Euler's equation, Euler's method, or Adam-Bashforth method, or predictor corrected method. So, therefore, but all these numerical schemes will be having the disadvantage of instability. There may be numeric, if the step size of numerical integration is not properly selected, then instability may be a problem. If the equations are stiff equations for stiff ordinary differential equations, none of this method will be can be utilized. Then you have to use the spatial algorithm like Gears method may be used. The stiff ODE means if the variation of dependent variable, a small variation of independent variable gives a large variation in of the dependent variable. So, that gives a that is called by the stiff ordinary differential equation. So, you require to have special algorithm for them. So, you could have all these shortcoming can be overcome by using this eigenvalue method. eigenvector method. That gives us more accurate and elegant method of solution, trouble free. So, what are the various subroutines one has to write? One has to have a subroutine of evaluation of the eigenvalues. That is not a problem. One can use the Horner's method. One can use the subroutines for evaluation of eigenvectors. So, eigenvalues, eigenvector, then matrix transpose of you have to remember, write a couple of line routines for matrix transpose, and then one has to go for the simple calculations like a matrix multiplication. So, using 4 such basic subroutines, one can utilize the eigenvalue eigenvector method in order to solve the complicated problems of linear ordinary differential equations in chemical engineering life, and can do away with the numerical complicacies or shortcomings of numerical integration. Next, we talk about the non-homogeneous solution of non-homogeneous first order ordinary differential equation, but with but it is they are non-homogeneous. In the earlier case we have solved they are homogeneous, and in this case we will be talking about the solution of non-homogeneous first order ODEs. Of course, they are IVPs. In fact, even boundary value problem can be broken down into series of ordinary differential equations by assuming the unknown the initial condition and then matching with the corresponding boundary condition. Anyway, so let us write down the set of non-homogeneous ODEs in a compact form, and that will be dx dt is equal to Ax plus b of t. In general, this is this term corresponds to non-homogeneous term, okay. So, this can be the non-homogeneous term can be constant term or it can be function of time, but this cannot be function of x. Then this term, the extra term in the additional term on the right hand side is called a non-homogeneous term. Then this set of equation has to be solved by subject to the boundary condition, the initial conditions that at x vector at time t is equal to 0 is given by this vector, represented by this vector x naught. Now, A is a real non-singular matrix and we know how to evaluate the eigenvalues and eigenvectors of this matrix, and for this matrix we can evaluate the eigenvalues, and let us say Z I forms a set of vectors which are nothing but the eigenvectors. And since eigenvectors are they form the independent set of vectors, we have already proved earlier these are independent set of vectors and they constitute a basis set. Therefore, any other vector in the domain can be expressed as a linear combination of the basis set vectors or the eigenvectors of the matrix A. Now, we assume the vector b t, b which is a function of t, is expressed as a summation of beta I, as a summation of as a linear combination of these vector the eigenvectors Z I, and the solution x t is expressed as combination of these eigenvectors Z I. So, we have to assume the form of the solution assume the form of a solution as x t is equal to z e to the power lambda t. We have proved that if this is the form of the equation, a form of the solution, we have proved earlier that lambda I corresponds to eigenvalues of A and Z I correspond to the eigenvectors of A. So, therefore, we have the eigenvalue problem A Z I is equal to lambda I Z I. So, lambda I is the ith eigenvalue and Z I is the corresponding eigenvector, and this eigenvalue problem is defined. Okay. So, next we write down the the equation dx dt is equal to a x plus b, and write down the solution, write down the expression of x. X is summation of c I z I. So, therefore, this will be summation d c I dt. If you remember, c I was a sole function of time. So, it becomes d c I dt. Z I is equal to a summation of c I, which is a function of t z I, plus summation of beta I times z I. So, therefore, one can bring this up on the left hand side and put everything under the summation. So, this becomes d c I dt z I minus summation of c I t a z I. Okay. So, matrix is an operator. So, we operate on z plus minus summation of beta I z I will be equal to 0. So, we have summation of d c dt z I, and we identify that this a z I is nothing but lambda I z I. So, therefore, this becomes c I t lambda I z I minus summation beta I z I is equal to 0, and all these summations are over the index I, runs from 1 to n for n dimensional problem. Next, we bring everything under the summation. So, it becomes so d c I dt minus lambda I c I minus beta I times z I equal to 0. And if we remember that what these z i's are, these z i's are eigenvectors and they are independent to each other, independent vectors, and they form a basis set. So, therefore, if these vectors are independent vectors and they are written in this form, the coefficient of all these vector has to be independently equal to 0 in order to satisfy this equation. So, therefore, we have the condition d c I dt minus lambda I c I minus beta I should be equal to 0 in order to satisfy this equation, because the eigenvectors are set of independent vectors. To satisfy this equation, all the corresponding individual coefficient must be equal to 0. So, we get an ordinary non-homogeneous first order equation, non-homogeneous first order ODE as d c I dt as a condition, d c I dt minus lambda I c I minus beta I, which is in general function of time. Now, this is a non-homogeneous PDE. this method, this ODE can be non-homogeneous ODE, ordinary differential equation. This ODE can be solved by the method of integrating factor. So, we multiply both the sides by integral e to the power minus lambda I dt. This is the integrating factor. So, this becomes e to the power minus lambda I t. So, we multiply both sides by e to the power minus lambda I t. So, this becomes e to the power minus lambda I t dci dt minus lambda I e to the power minus lambda I t ci minus beta I e to the power minus lambda I t is equal to 0. So, we can combine these two parts. So, it will be d dt of e to the power minus lambda I t times c is equal to beta I e to the power minus lambda I t. So, we can integrate this out. So, it will be 0 to t, beta I is in general function of time. So, 0 to t dt. So, we should write it in the next step. Okay. So, it will be in the next step you will be getting 0 to t d of e to the power minus lambda I t times c is equal to integral beta I t e to the power minus lambda I t dt 0 to t. So, we can get this integral evaluated. So, this will be giving you that after evaluation of this integral you will be getting c I. Okay, we will be having the subscript I in all the cases of c I of the c's. So, therefore, after integration you will be getting c I e to the power minus lambda I t minus c I at time t is equal to 0, at time t is equal to e to the power 0 becomes 1 is equal to 0 to t beta I t e to the power minus lambda I t dt, and you will be getting c I as a function of time as c I naught e to the power lambda I t plus e to the power lambda I t 0 to t beta I e to the power minus lambda I t dt. So, we will be getting this expression as the final solution, and let us see how the c I naughts are obtained. C I naught, the vector c I naught is obtained from the initial condition, and what is the initial condition? We know the vector x naught, that means all the solutions were known as the initial condition of the initial at time t is equal to 0. So, this vector can be expressed as a linear combination of independent vectors z I. So, therefore, one can obtain this by combining this with the eigenvectors of A transpose. So, now if y I is a set of eigenvectors for A transpose, then inner product of x naught and y 1 should be given as, we take the inner product of this equation with respect to y 1. So, this becomes c I naught inner product of z I and y 1. In fact, if you open up this series, then we will be getting c 1 0 inner product of z 1 y 1 plus c 2 0 inner product of z 2 y 1 plus like that, and c n 0 inner product of z n y 1. Now, z 1 and y 1 we have already proved that eigenvectors of A and A transpose will form a bi-orthogonal set. So, inner product of z 2 and y 1 will be 0, inner product of z and y 1 will be y 1 will be equal to 0. So, only one term will survive in this summation, that will be C 1 0 inner product of z 1 and y 1. So, in that case what we will be getting as C 1 0 is that, so we will be getting C 1 0 is equal to inner product of x naught y 1 divided by inner product of z 1 and y 1, and we can get as x 0 transpose y 1 divided by z 1 transpose y 1, and ultimately you can get the generic form of C I naught as inner product of x naught of and y I divided by inner product of z I and y I. So, you can put into the matrix in vector multiplication form, matrix multiplication x 0 t y I z I transpose y I. So, that will be the form of coefficient synthesis in the above solution. And next we will be talking about the other parts of the solution. So, the C I naught vector will be determined by this, because we can evaluate the eigenvectors of A transpose, we can evaluate the eigenvectors of A, we know the initial condition vector. So, all of these coefficients C I naught will be calculated. Next is the calculation of beta I. Next step is calculation of beta i's. So, if you remember, the vector b as a function of time can be expressed as linear combination of the eigenvectors of A as beta I z I. Then we can take the inner product of this equation with respect to y I of above equation with respect to y I. So, you will be getting y I inner product of y and b is summation beta I z I and y I, beta I being a constant. So, it will be summation beta I inner product of z I and y I. Again one can open up this summation series and see what you get. So, it will be let us consider for 1. So, beta y I inner product of y n and b, you will be getting beta 1 inner product of z 1 y 1 plus beta 2 z 1 y I. Okay. So, beta 2 inner product of z 2 y I plus beta 3 inner product of z 2 and y I. Like that, you will be getting beta I inner product of z I and y I. So, since z i's are the eigenvectors of A and y I are the eigenvectors of A transpose, they form the bi-orthogonal set, and we have already proved that except I is equal to j, they will be their inner product of the individual eigenvectors will be equal to 0. So, these will vanish, these will vanish, these will vanish, only this term will survive out of this summation. So, therefore, in general one can evaluate beta I is summation of y I b divided by inner product of y I z I. Inner product of z I y I is identical to inner product of y I and z I. So, this will be nothing but inner product the multiplication of y I transpose and the vector b, and this will be multiplication of y I transpose and vector z I. So, that is how the coefficients beta I can be evaluated. So, once you obtain the expression of beta I, once you obtain the expression of C I, then you can construct the complete solution as So, the complete solution, if you look into the complete solution, we wrote CIT is equal to Ci naught e to the power lambda I t plus e to the power lambda I t 0 to t beta I e to the power minus lambda I t dt. So, therefore, where the coefficient C I naught can be expressed as inner product of x naught and y I divided by inner product of z I and y I. So, this will be x naught t y I, we have already written this. So, this will be z I transpose y I, and beta I we have already obtained as y I transpose b divided by y I transpose z I. So, once we get this, we can get the solution of CIT, and we will be getting the complete solution. Okay. Next, we will be with this theoretical formulation of solution of non-homogeneous ordinary differential equation by eigenvalue eigenvector method, we will be taking up one particular example, a chemical engineering application example, and see how this problem will be solved by using this eigenvalue eigenvector method. So, the example that we will be talking about is highly relevant for chemical engineers, and this is the problem of reaction engineering. And we will be taking up a series reaction, consider a series reaction in a CSTR, and I have already discussed what a continuous start tank reactor is in earlier classes. So, consider a series reaction in a CSTR. So, you will be having a reaction like this, A going to B going to C, and they are elemental reaction, let us say, and the rate expressions are given as first order rate expression. The feed concentrations was given CAF as 1 gram mole per cc, and initial conditions were at time t is equal to 0, the concentration of A, B, C were given by this vector 1 gram mole per liter, 0 gram mole per liter and 0 gram mole per liter. So, at time t is equal to 0, there was nothing in the system except Ca feed, that was 1 gram mole per cc, and the K1 and K2 values are given. K1 is given by 2 second inverse, K2 is given as 3 second inverse, and tau, that is residence time, and it is defined as volume divided by the volumetric flow rate. So, volume will be in meter, volumetric flow rate will be meter cube per second. So, it will be second, and this tau will be 4 second. Okay. So, we have now in a position to write down the species balance equation. We write it as tau residence, the time. So, we write down the species balance equation. This will be dCA dt is equal to 1 by tau CAF minus CA minus K1 times CA, that is the A balance. B balance will be 1 by tau CBA B feed minus CB plus K1 CA minus K2 CB. So, this is the accumulation term, this is net material in minus net material out minus plus rate of generation here, and in the case of A it will be consumption. In fact, this is a combination of rate of generation and rate of consumption, because B is produced at the rate K1 Ca and it will be consumed at the rate K2 times Cb. So, dCc dt can be written as 1 by tau Cc final Cc in the feed minus Cc plus rate of generation K2 Cb. So, we can write it more amenable form, dCa dt will be minus 1 by tau res minus K1 times Ca plus Caf divided by tau dCb dt can be written as K1 Ca plus minus 1 by tau minus K2 times Cb plus Cb feed divided by tau resistance, and dCc dt can be written as K2 Cb minus Cc by tau plus Ccf by tau. So, you will be having the form of non-homogeneous set of non-homogeneous ordinary differential equation. So, this will be the dx dt part, where the component were Ca, Cb and Cc. These were the coefficient matrix, and these terms combining these terms correspond to the non-homogeneous part. So, therefore, one can get these equations. So, we can write it as dC dt in a more compact form matrix notation, minus 1 by tau minus K1 0 0, K1 minus 1 by tau minus K2 0 0, K2 minus 1 by tau times C plus the vector Caf divided by tau, Cbf divided by tau and Ccf divided by tau, where the matrix C is the vector C is basically given by Ca, Cb, Cc. So, it has 3 elements. Now, we can write down this in a compact form, dC dt d tau is equal to Ac plus B, where the B vector is given by this. So, this is a B vector, and the coefficient matrix A can be given as, just put all the values. So, if you put all the values, this becomes minus 2.25 0 0, 2 minus 3.25 0 0 3 minus 0.25. Put all the values there. So, you will be landing up with the coefficient matrix like this. Now, we can, this is a 3 by 3 matrix. So, we can we can evaluate the eigenvalues of this matrix, and we can obtain the eigenvectors. So, for the eigenvalues, what we do? We put determinant of A minus lambda I is equal to 0. So, you will be getting a polynomial of lambda, and this polynomial will be a third order polynomial, and you will be getting 3 roots, those will be corresponding to the eigenvalues. So, lambda 1 is equal to minus 2.25, lambda 2 is equal to minus 3.25, and lambda 3 is equal to minus 0.25, and the corresponding. So, these are the eigenvalues. corresponding eigenvectors will be Z1 and it will be 1, 2, minus 3 transpose. I am not again deriving it, we have already seen in the earlier examples how to evaluate the eigenvalues and corresponding eigenvectors of a square matrix. Z2 is 0, 1, minus 1 transpose and Z3 is 0, 0, 1 transpose. We can get the eigenvalues of the transpose matrix will be identical, that we have already proved earlier, and we can get the eigenvectors of A transpose, and these will be y1 is 1, 0, 0 transpose, y2 is minus 2, 1, 0 transpose, and y3 will be 1, 1, 1 transpose. So, these will be the eigenvectors of A transpose. So, we can write the compact notation that dC dt is equal to minus 2.25 0 0 2 minus 3.25 0 0 3 minus 0.25 times the vector c plus the vector 0.25 0 0. So, therefore, this is the set, this is the non-homogeneous term, this is the A, this is B. So, dx dt equal to in the form of x plus b, this is the non-homogeneous term. Now, we are going to solve this equation. So, our non-homogeneous vector becomes 1 by 4 0.25 0 0 and we write beta b is summation of beta I z I, we write x as summation of C I z I, where x is the solution, x is the solution matrix, solution vector. So, therefore, you can evaluate, since all these eigenvalues and eigenvectors of A and A transpose have already been developed and derived, we need not to, we just go ahead with the solution procedure. So, if you write down the expression of beta I, this becomes y I transpose times b, y I transpose times z I, and the expression of C I as a function of t, if you remember, this becomes C I 0 e to the power lambda I t plus e to the power lambda I t 0 to t beta I e to the power minus lambda I t dt. So, therefore, we can if you remember the expression of the vector C I naught, the element of the vector C I, it will be y I transpose x naught divided by y I transpose z I, where x naught were nothing but the vector which C A f, C B f and C C f, the initial values. So, therefore, C 1 0 will be nothing but y 1 transpose x naught divided by y 1 transpose z 1. So, this becomes 1 0 0, this becomes 1 0 0, that is the initial value vector, divided by 1 0 0, that is y 1 transpose, and z 1 will be 1 2 minus 3, that is the first eigenvector of the matrix A, and this becomes C 1 0 becomes 1 plus 1 divided by 1. So, it will become 1. So, all the other terms will be 0. Similarly, we can evaluate that C 2 0 and C 3 0. If you do that, C 2 0 turns out to be y 2 transpose x naught divided by y 2 transpose z 2, and this becomes minus 2 1 0 1 0 0, and this will be minus 2 1 0 0 1 minus 1. So, this becomes minus 2, this becomes 1 divided by 1. So, it becomes minus 2, and C 3 0 becomes y 3 transpose x 0 divided by y 3 transpose z 3, and this becomes 1 1 1 1 0 0 divided by 1 1 1 0 0 1, that is the third eigenvector. So, this becomes 1 and this is also 1. So, it becomes also 1. So, now you are in a position to evaluate the coefficient beta 1. So, beta 1 becomes y 1 transpose times b divided by y 1 transpose times z 1. So, this will be 1 0 0, that is y 1 transpose, and b will be 1 by 4 0 0 divided by 1 0 0 1 2 and minus 3. So, this becomes 1 by 4 divided by 1. So, this becomes 1 by 4. Similarly, one can get beta 2 as y 2 transpose b divided by y 2 transpose z 2, and this becomes minus 2 1 0, it will be 1 by 4 0 0 divided by y 2 transpose and z 2. So, minus 2 1 0 and z 2 will be 0 1 minus 1, that is the second eigenvector. This will be equal to minus half divided by 1. So, it will be minus 1 by 2. Similarly, we can have beta 3 is y 3 transpose b y 3 transpose z 3. So, this will be 1 1 1 1 by 4 0 0 divided by 1 1 1, that is y 3 transpose, it will be 0 0 1, and this will be 1 by 4 divided by 1. So, it will be 1 by 4. So, now you are in a position to get the coefficient C 1 t. So, C 1 t will be e to the power minus 2.25 t plus e to the power minus 2.25 t. If we look into the solution, this becomes 0 to t 1 by 4 e to the power 2.25 t dt. So, ultimately, after getting into the integration carried out, the solution becomes e to the power minus 2.25 t plus 1 by 9 1 minus e to the power minus 2.25 t, and you will be getting C 2 t as minus 2 e to the power minus 3.25 t minus 2 by 13 1 minus e to the power minus 3.25 t, and C 3 t will be e to the power minus 0.25 t plus 1 minus e to the power minus 0.25 t. So, we are in a position to get the coefficients C 1, C 2, C 3. Next set we are going to get the final solution. If you remember, the final solution was given by the solution vector x is summation C I Z I. So, you will be getting C A, C B, C C, is equal to C 1 Z 1 plus C 2 Z 2 plus C 3 Z 3. So, you have the coefficient that we have already evaluated C 1 as a function of time, you have just evaluated just now. Just put the value of Z 1, 1, 2 and 3 plus C 2, C 2 we have already evaluated that 0, 1, minus 1 plus C 3 we have already evaluated the expression of C 3 and Z 3 will be 0, 0, 1. So, therefore, you are in a position to get the value of final solution. Now, we will be putting C 1, C 1 is e to the power, actually both it will be C 1 times 1 plus C 2 times 0 plus C 3 times 0. So, they will contribute nothing. So, it will be minus 2.25 t plus 1 by 9 1 minus e to the power minus 2.25 t, that is the expression of C 1. And if you look into the expression of C b, it will be 2 times C 1 plus 1 times C 2 plus C 3 into 0. So, we have already evaluated 2 C 1 and C 1 and C 2, put them here 2 e to the power minus 2.25 t minus e to the power 2 minus e to the power minus 3.25 t plus 2 by 9 1 minus e to the power minus 2.25 t minus 2 by 13 1 minus e to the power minus 3.25 t. So, we can just simplify this equation and get the final expression of C c. The C c will be simply 3 times C 1 minus C 2 1 times C 2 plus 1 times C 3. So, ultimately you will be getting minus 3 e to the power minus 2.25 t plus 2 e to the power minus 3.25 t plus e to the power minus 0.25 t minus 3 by 9 1 minus e to the power minus 2.25 t plus 2 by 13 1 minus e to the power minus 3.25 t plus 1 multiplied by 1 minus e to the power minus 0.25 t. So, that gives the final solution of C c. So, we get the expression of concentration of A, B and C as a function of time. So, we can get the steady state solution also. Steady state solution is obtained when t tends to infinity. So, once we just put t tends to infinity in the solution, so we get the steady state solution, and the steady state values of C a at the steady state is 1 by 9 molar gram mole per liter, and C b steady state is 8 by 117 and C c steady state is 32 by 39. So, one can get the transient non-homogeneous ordinary differential equation, and the eigenvector method can be fundamentally utilized to solve elegantly the set of ordinary differential equation homogeneous and non-homogeneous both, and also there should be the initial value problem. So, IVP homogeneous and non-homogeneous ordinary differential equation can be solved by this using these eigenvalue eigenvector methods. Next, in the we will be, since we can see that since this the solution contains the form e to the power minus lambda t. Now, depending on the sign of lambda, one can expect the solution, whether the solution grows in time or decays with time, because the solution will be in the form of e to the power lambda t. So, sign of lambda plays a crucial role, and therefore, this eigenvalue and eigenvector method plays a very crucial role in determining the stability of ordinary differential equations, and which are basically representing the chemical engineering system. So, chemical engineering systems can also be directly related to the signs of the eigenvalues. So, therefore, we stop in this class, and the next class we will start looking into the stability of the chemical engineering system depending on the sign of the eigenvalues, and how these will be quantified and put in a more formalized mathematical way to evaluate the stability of the system. Thank you very much.